Hello, my name is Nicholas, and I will be discussing isotopes. An atom has three parts: protons, which have a positive charge and dictate the element number; electrons, which have a negative charge and dictate the ion and the charge of the element. And then there are also neutrons, which have no charge or a neutral charge and dictate the isotope of the element. And each of these parts has a certain amount of weight, very negligible on our scale, but it does add up because there's a certain amount in every atom. Electrons have a very negligible weight. It's 0.000549 amu, and again, that's very negligible. Protons have a weight that it is very significant to the atom, but it's not relevant to the isotope because you can't change that weight without changing the element. Because if you increase the number of protons, you increase the number of the element. But protons have a weight of 1.007316 amu. Then there are neutrons. That's what is relevant to isotopes. They have a charge. Um, they have a neutral charge, but they have a weight of 1.008701 amu, and they add to the atom if you drop another one on. It doesn't change the charge of the atom or the element number, so it doesn't affect the chemical properties of the element other than a slight delay in reaction time with other elements, but it does increase the weight. So isotopes, I made my own definition of isotope, and I made the before looking at any other sources within the same couple of minutes. My definition was atoms of the same element with a different weight caused by a differing number of neutrons. Then I looked at dictionary.com, whose definition was any of two or more forms of a chemical element having the same number of protons in the nucleus or the same atomic number but having different numbers of neutrons in the nucleus or different atomic weights. So my definition came close. It had a very similar meaning. And isotopes, when you name them, you generally don't have a name for them, like a special name. Hydrogen isotopes, the first three do have names. Protium is for regular hydrogen with one proton and one electron. D, or, well, D is the atomic symbol, and it's for deuterium, and that has one extra neutron with the proton and the electron. And it is also stable. It's not radioactive, and neither is protium. And then there's tritium, which has another neutron, and it is radioactive. Isotopes of the other elements are just named according to their atomic symbol and or name with the number of the weight attached to it. The weight is stated in the number of amus, like argon 40, potassium 40, potassium 39, oganesson 294. Those are all examples. And I have some examples of isotopes that can actually come up in the real world. There's potassium 40, which is, it's a kind of potassium, and we have potassium in things we eat, like bananas, and a measurable amount of the potassium in nature is radioactive. It's very small, it's under 1%, but it is measurable, which makes it significant. And there's also uranium and plutonium have isotopes that are commonly referred to. Uranium 238 and 235 are used in bombs and reactors. Well, uranium 235 is concentrated in a certain amount of the uranium. And then plutonium-239, for plutonium-239 is used in weapons and reactors. Weapons being, of course, nuclear weapons, fission bombs, and reactors being nuclear reactors. And plutonium-238 is used in radioisotope thermoelectric generators, or RTGs, which can be used. It's like a portable power generation device, and they used to be used for buoys that needed lights, and now they're mostly used for space probes. And then there is hydrogen, of course. Regular hydrogen is used for many things. It's in water, it's in hydrocarbons like plastics and oils, and most life has hydrogen in it. It's also, the sun and Jupiter are made up of a lot of hydrogen. And then there's deuterium, which is used in cooling nuclear reactors, and tritium, which is used for glowing phosphors. Like, if you need something to glow for a very long time, you can add tritium to phosphors and it'll glow, like for watch hands. But it's very safe. Tritium isn't very radioactive, so the radiation can be contained very easily with glass, and it doesn't hurt you if it's in the glass. And if the glass broke, it wouldn't be very significant, so it wouldn't hurt you unless you just stayed around it for a long time. And then tritium is also used in nuclear applications. Those are just some of the examples for deuterium and tritium, and hydrogen too. I don't know all of them. So, if you like this video, be sure to subscribe, leave a comment suggesting future videos, and goodbye.